Welcome to this explainer. Today, we're diving into something you probably look right past every single day, the automotive bolt. I mean, it seems completely trivial, right? It's just a simple piece of metal. But today, we're going to completely reframe how you see it, because the creation of this humble little fastener is actually a massive marvel. It is a story of heavy geological extraction, intense metallurgy, global logistics, and absolutely cutting-edge mechanical engineering. To really put the scale of this into perspective, just think about this number for a second. 30,000. That staggering figure represents the average number of individual fasteners holding together a standard compact passenger sedan. And hey, if you drive a larger SUV, that number can easily climb to an astonishing 50,000. Now, modern electric vehicles do use about 6% fewer fasteners, but they still rely on tens of thousands of these critical components to keep you safe at highway speeds. And the crazy thing? Every single one of them has an epic origin story. So here is our roadmap for the journey. We'll be covering earth to pure iron, refining high-strength steel, cold heading and threading, global transit and emissions, precision assembly, and finally, surviving vibration and fracture. All right, let's jump straight into part 1, earth to pure iron. The physical existence of our fastener actually begins deep within the Earth's crust as iron-bearing rock, primarily magnetite or hematite. After heavy mining machinery excavates the raw ore, we hit an immediate roadblock. It is heavily contaminated with acidic silica and alumina, which we call gangue. So to liberate the iron, we have to rely on some sheer physical and chemical genius. First, we literally pulverize the rock using massive jaw and cone crushers, a process called comminution. Once it's ground into a fine powder, we have to separate out the iron. If it's magnetic magnetite, we just use low-intensity magnetic separation to pull it out. But for non-magnetic hematite, well, we use a brilliant physicochemical process called reverse ketonic flotation. We mix the ore into a watery pulp and add highly specific chemicals. We use starches to chemically depress the iron oxides, keeping them at the bottom, while amines act as collectors that grab onto the silica gangue and float it right to the surface to be skimmed off. It's incredible. This reduces the silica content to a super tight 5 to 8% window. But wait, before we can smelt this newly concentrated iron, we have another problem. Those fine particles have to be clumped back together. Otherwise, the dust would literally choke the gas flow inside a massive smelting furnace. We fix this through a process called sintering. We blend the fine ore with limestone flux and coke and heat it on a continuous strand to a blistering 1300 to 1480 degrees Celsius. This slightly melts the surface of the particles, binding them into a porous, mechanically tough chunk that is totally ready for the blast furnace. Moving right along to part 2, refining high-strength steel. To turn that concentrated iron ore into usable metal, it's typically shipped across the ocean to integrated plants and melted inside towering blast furnaces to create pig iron. Now, pig iron is packed with 3 to 4% carbon, making it way too brittle to be a fastener. Historically, we refine that pig iron into high-strength steel using a basic oxygen furnace. Here, a lance injects high-purity oxygen at supersonic speeds to literally burn off the excess carbon. The chemical reactions are so wildly exothermic, meaning they create so much heat that solid scrap steel has to be dumped in just to absorb the excess energy. But things are shifting. Today, to lower greenhouse gas emissions, the industry is increasingly using the circular electric arc furnace. Instead of using raw iron and coal, this furnace uses high-voltage electric currents to melt down sorted scrap steel. Ultimately, making the perfect fastener is all about getting the chemical recipe exactly right. For automotive screws, the preeminent alloy is SAE 10B21 boron steel. Look closely at the microscopic fraction of boron used here. Just 0.0035%. That is a mind-blowing scale of precision. It's basically a rounding error. But that tiny fraction of boron is an absolute game changer. It blocks the formation of soft ferrite inside the metal, which guarantees the steel will harden completely through its core when we heat treat it later. And it does this while letting us keep the overall carbon content low, meaning the steel stays soft and bendable right now, which is exactly what we need for the next step. Okay, part 3, cold heading and threading. Let's hit the factory floor. So we've got our carefully crafted steel rolled into long wire rods. But you can't just smash steel into the shape of a screw without prepping it first. It has to go through a sequence we call SAPPD. First up, spheroidized annealing. We use heat to turn the hard internal structures into soft spherical particles, making the metal as ductile as possible. Next is pickling, where we use acid to clean off any mill scale. Then, a zinc phosphate layer is added to hold lubricants. And finally, it's drawn through dies to get the absolute perfect diameter. The steel is now primed and ready for violence. And I do mean controlled violence. We feed this wire into high-speed machines that strike the metal with immense compressive force, forming the head of the bolt at room temperature. We call this cold heading, and these machines can spit out up to 400 pieces a minute. But we don't just do it because it's fast. Think about subtractive machining. Cutting away metal actually severs the internal grain structure. Cold heading, on the other hand, forces the metal to flow plastically. It keeps those internal grain lines completely continuous, totally eliminating weak points, and it physically hardens the steel just from the sheer strain of the deformation. The exact same logic applies to the threads. We don't cut the threads, we roll them. The shank of the bolt is basically squeezed between incredibly hard dies that press the thread pattern right into the metal. And this is so crucial for engineering efficiency. Squeezing the material induces severe compressive residual stresses at the roots of the threads. Since microscopic cracks need tensile stress, or pulling apart, to grow, these compressive stresses actively fight off fatigue cracks. Plus, because we aren't shaving away any metal, we literally save 15 to 20% of the raw material by weight. That is massive at scale. Which brings us to part 4, global transit and emissions. Because manufacturing is highly globalized, regions like Taiwan, historically known as the Screw Kingdom, with an industrial cluster of over 1,800 specialized facilities, export over 93% of their fasteners. This kicks off a massive transoceanic journey. To move literally millions of tons of heavy steel, sea freight is the absolute only viable option. Yes, there's port congestion, and yes, it takes a long time, but its carbon intensity is remarkably low compared to road trucking or the absolutely massive emissions of air freight. Still, because of the sheer scale of global trade, maritime shipping does account for about 3% of global greenhouse gases. And international regulators are actively addressing this right now. The EU has introduced something called the Carbon Border Adjustment Mechanism, or CBAM. Basically, it places a carbon tariff on the embedded emissions of imported goods, and that includes steel fasteners. Starting in 2026, manufacturers have to buy certificates to cover the emissions generated during the entire life cycle we've just been talking about. This policy is fundamentally forcing fastener makers to adopt green energy, utilize those electric arc furnaces we discussed, and aggressively track their supply chain data just to stay in the game. Part 5, Precision Robotic Vehicle Assembly. So our fasteners have survived the forge, crossed the ocean, and finally arrived at the automotive assembly plant. This is where robots, equipped with smart electric screwdrivers, integrate those 30,000 pieces into a functional vehicle frame. Now, you might think tightening a bolt is simple, right? Just spin it until it's tight. Well, actually no. Why is simply applying a set torque not enough to secure a critical vehicle joint? Get ready for this. 85 to 90% of the rotational energy applied by the robot is completely wasted. Seriously. It just dissipates in overcoming the friction under the bolt head and inside the threads. Only about 10% actually goes into stretching the bolt to create clamping force. Because friction is so incredibly unpredictable, it can change from a speck of dust, a tiny drop of oil, or a shift in room temperature. Standard torque-controlled fastening can result in huge variations in how tightly the joint is held together. You definitely don't want that on your engine block. So for critical joints, engineers use torque angle fastening. First, the robot applies a low, snug torque just to pull the metal plates together. Then it rotates the bolt a precise number of degrees. By focusing on the angle of rotation rather than the twisting force, it basically ignores friction entirely. It literally stretches the bolt past its yield point into the plastic deformation zone, guaranteeing a near-perfect, rock-solid clamp load every single time. Finally, we reach part 6, surviving vibration and fracture. Once a vehicle hits the road, the real test begins. These fasteners will experience cyclic transverse vibrations every single time the car hits a bump, constantly trying to shake the nuts loose. Traditional friction locking, like those nylon insert nuts you might have seen, often degrades under extreme heat and continuous vibration. So engineers deploy mechanical wedge locking technologies instead, like Nordlock washers. These are brilliant. They use a clever set of dual washers with inner cams that are actually steeper than the pitch of the thread itself. So when vibration tries to loosen the bolt, the rotation forces the steep cams to slide against each other, which actually pushes the washers apart. It literally uses the energy of the vibration to increase the clamping force. It turns the enemy into an ally. But vibration isn't the only enemy out there. There is a silent, invisible killer called hydrogen embrittlement. It is a catastrophic, delayed fracture phenomenon where high-strength bolts can just snap in half days or even weeks after it's been assembled. No warning. For this to happen, 3 exact thermodynamic conditions have to perfectly align. First, you need a hard, susceptible material, usually over 34 Rockwell C. Second, you need a source of atomic hydrogen, which is actually often introduced during the acid cleaning or electroplating processes we talked about earlier. And third, you need sustained tensile stress from the tightened joint. Here's what happens. The hydrogen atoms are so tiny, they literally migrate through the empty spaces in the steel's crystal lattice, gathering at high stress points and drastically weakening the metal from the inside out. So how do we defeat this invisible atomic threat? We bake them, literally. Engineers mandate that freshly plated high-strength fasteners be placed in specialized ovens at 190 to 230 degrees Celsius for anywhere from 8 to 24 hours. The intense heat speeds up diffusion, forcing the trapped hydrogen to safely escape out of the metal before the fasteners ever ship to the assembly plant. So through this absolutely incredible integration of intense metallurgical chemistry, precision fabrication, carbon-conscious logistics, and advanced assembly engineering, the automotive fastener ensures the structural integrity of your vehicle. It is so far from just a simple piece of metal. The next time you get behind the wheel and merge onto the highway, I really want you to ask yourself, are you just driving a car? Or are you hurtling forward in a masterclass of physics held together by 30,000 highly engineered hidden heroes? Thanks for joining me on this explainer. Keep learning, keep looking closer at the details, and I'll catch you in the next one.